So thank you very much for being here this afternoon. I'm a bit concerned about this evergreen stuff because it makes me feel old, sort of. Maybe some of you still remember the first presentation I gave here. That was right about after Kohl was elected, but let's just go on with this. So, please allow me to introduce myself. My name is Gerhard Loschwitz. I live in Austria's beautiful capital, Vienna. If you ever hear me speak German, you will realize that I was not born in Austria originally, but I was born in a very small village near the German city of Düsseldorf. So it's in the very western part of Germany. Some of you might have read an article I wrote in one of the numerous magazines. I write articles for the German Linux magazine. I write articles for the German admin magazine. I'm also a Debian developer. I've been quite a passionate packager for some time now. I mainly work on the Linux HA cluster stack, so pacemaker, CurrSync. Whenever somebody of you uses pacemaker or CurrSync on Debian, then it's fairly certain that these packages have gone through my hands at some certain point in time. Now, please don't throw something at me. I'm just a packager, not the guy writing the source code. And besides, I am also a very regular speaker at conferences, so maybe you've seen me at one or another conference in the past. I am a passionate bowler. I like to bowl, so if anyone of you ever comes to Vienna and wants to play a round of bowling, then please drop me a note, and that's going to be doable. And if besides all the free time activity I have, I still have some time to do actual work, then this is the company I work for. We are OSDC. We are active mainly in 3 different fields of business. The first being Linux and high availability, so we're doing pacemaker and CurrSync and all that stuff, consultancy. We are also active in OpenStack cloud deployments, so we can do cloud installations based on OpenStack. And what we also do is we do quite some development, we do quite some research with regards to storage, scalable storage and distributed storage, and after all, that is what I'm here for, and that is why I'm speaking in front of you right now. So, before we start with this, please just one little question to the audience. Who of you guys is running centralized storage in one way or another? So ASAN storage or anything that comes close to that. Okay, and who of those guys who have just raised their hands have ever run into a scenario where you ran out of space on that centralized storage? Okay, so you're in the right track then. Welcome again. And first of all, let's start discussing this term, this word scalable storage a little bit. I will assume that you guys know what storage is. I will also assume that you guys have a rough idea of what scalable means. However, I would like to elaborate a bit on the term of scalability. Scalability, in fact, comes in 2 dimensions, comes in 2 different types. One type being scale up. Scale up, in fact, is adding hardware, adding more hardware to already existing machines, or for that matter, replacing existing machines with the same amount of hardware that is, however, more capable than the previous hardware was. So if you're doing scale up and you have one server, then the setup you have will look like this before the actual scale up process. And once you're done with doing the scale up thing, it will still look like this. You will still have a single server, but that single server is probably going to be more capable, and it will be able to provide more resources to your actual clients. So in fact, you have one server before and you have one server afterwards. The problem with scale-up is that scale-up quickly comes to its limits, particularly when it comes to adding resources to already existing machines. You simply cannot put an infinite amount of hard disks, for example, into a server, because it will have a defined number of slots for hard disks it can take. It will have a defined number of memory sticks you can put into it. It will have a defined number of CPUs you can insert into this. You might be able to add faster CPUs by replacing the existing ones, but at some certain point you will be at the end of this, and you will not be able to add more hard disks, more RAM, more CPU to the machine that you have. Contrary to this, there's scale out. Scale out, in fact, means adding new servers to the ones you already have. So this is a scale out setup before the actual scaling. And once you're done with doing scale out, you have particularly something like this, where you have the same servers, or maybe servers that are just a little bit faster than the one you already had, but you have many of these. You have more than one, and you can distribute the load of your setup onto these 3 servers now, instead of having it applied to only one server at a time. In fact, scale-out is hip. Everybody is doing scale-out these days. Web servers have been doing scale-out for years. These are the typical load balancer setups that you will all know, I guess. Databases have started to do scale-out. We have Galera for MySQL, where you can run an infinite number of MySQL servers in multi-master mode, so that you can access every MySQL instance in read and write mode. Even I personally do scale-out, as you can see. However, the problem with storage is that at some certain point in time, development with regards to storage has just stopped. We don't have any real scale-out for storages, or at least we didn't have storage scale-out until some time ago. Now, why is it so difficult to extend storage, to extend the idea behind storage to something that allows for scale-out? We have the block problem. The block problem is called like that, particularly because the inability to do scale-out for storage is caused by the standard block-based architecture of storage devices. If you go to a computer store and you buy any arbitrary storage device, you will not be able to use it in a meaningful way at the beginning, because you could write something down on the device, but at a later point, you wouldn't be able to find the information that you have just written. So you need something to help you to organize the actual data storage device. We do know these helpers as file systems. File systems allow us to manage a block-based storage device in a meaningful way. And the problem that we have when using file systems is that file systems are closely bound to the borders of the underlying storage device. So if you have a file system and you have that attached on top of a hard disk drive and you have the user space accessing the file systems, you simply cannot cut the file systems into stripes and distribute these stripes over different servers in your setup, because standard Linux file systems don't allow for this. Standard file systems in Linux do not allow you to create scale-out setups, to create distributed setups. And that's a problem, because for scale-out setups, we need distributed setups. We need to distribute the stuff we have over numerous servers, because if we cannot do that, we cannot create scale-out setups. Which means that blocks, in fact, are a somewhat not so well-fitting solution for creating scale-out setup with storage, with regards to storage. In fact, they're not usable for the idea that we have. Which brings us to object stores. Object stores Object stores follow another idea. Object stores will basically cut any information, any piece of data you upload into the object store into small pieces, and these small pieces will then be converted into binary objects. The advantage you have is that object stores organize themselves internally based on this object idea. So please don't get me wrong, even object stores at some point need block storage devices to contain the actual information that is stored in the object store. However, they organize themselves based on the idea of binary objects. So the borders of the underlying file system and the actual blocks on the hard disk drives are not really important to the object store, because all the object store needs is the internal object structure that it has. Binary objects can easily be cut apart, and these parts that you then get can simply be distributed over the numerous disks that you have. No matter how many file systems you have, no matter how many servers there are, you can cut binary objects into pieces and distribute these over the numerous disks that you have. And that brings another advantage, because in fact, the interface that your object store exposes to the user land doesn't really matter anymore. It's not of interest whether this is an actual file system driver, whether it's a block device, whether it's something that allows direct access to the blocks, to the objects in this case. You can just use an arbitrary number of interfaces there. And this brings us straight into Ceph, because Ceph, in fact, is a solution that makes use of this advantage very well. Ceph originally was a PhD thesis. It was written by Serge Weil for the University of Santa Cruz in California, together with some of his colleagues. And interestingly enough, the idea of Ceph is not as new as it may look like, because the project itself has been there for years. Only in the last 12 months, the company that is driving the development of Inktank has started to actually market this product. Could I get another microphone? This is making me nuts. So I need to keep this away from my mouth a bit further. Okay, so as said, it was originally a PhD thesis. It's by now done, and Inktank, the company doing development behind Ceph, has now just started to market this product. We will see that Ceph, in fact, is not a single product, but it is a number of components that together form the Ceph object storage solutions. And we will now take a closer look at the different components that we have. And the most important one, obviously, is the object store itself. So the component in Ceph that allows to store data in a binary manner in form of binary objects. The object store in Ceph used to be called Rados. Some of you might know this name maybe. In fact, Inktank is trying to rename Rados to Ceph. So when I'm using Ceph or Rados in the course of this presentation, I'm basically meaning the same thing. The file system that used to be known as Ceph by now is known as CephFS. If I use Ceph or Rados in the course of this presentation, then please keep in mind that in both cases I'm referring to the object store per se. So to the piece of the software that allows to store data in form of binary objects. Rados is an acronym. It's the acronym for Redundant Autonomic Distributed Object Store. And this alone is a very well explanation of what Rados can actually do. It's redundant, meaning that every binary object you store into the object store, in fact, is replicated automatically. It's autonomic, which means it takes care of itself. It's distributed. The number of devices that can participate in a Rados object store is unlimited, and it's an object store, so it's exactly the kind of software I was referring to earlier. Rados consists itself out of two components, the first component being the so-called OSDs. OSDs are OSD is the acronym for Object Storage Daemon, and in fact OSDs in Ceph are the data tanks. So every piece of information you upload into Ceph will be stored on an OSD, will be stored on an Object Storage Daemon, because as I already mentioned, obviously even an object store at the end needs some block devices, some block storage devices to contain the information uploaded into the object store. The general assumption is that every hard disk present in your Ceph installation is going to be a single OSD. So if you have a server that can hold 8 hard disks, that server will basically have 8 OSDs. In fact, the Ceph developers actively recommend against using technologies like RAID on the hardware level, because the general assumption is that everything related to reliability and redundancy is taken care of by Ceph on its own, and using hardware redundancy solutions in this case is something that would just waste space on the local servers. Every Unix file system holding device, every block storage device holding a Unix file system can be an OSD if the OSD supports user extended attributes. And the number of OSDs that a Ceph cluster, that a Ceph installation can hold is basically unlimited. So I can have numerous of these. I can have numerous of these distributed over a countless number of servers. I'm just totally free to choose how many OSDs I want. Second component we have in Ceph are the so-called monitoring servers, usually referred to as MONs. MONs have 3 different tasks. First of all, based on the Paxos algorithm, they take care of the cluster quorum, and by that avoid split brain scenarios. So if a monitoring server in Ceph cannot see enough other monitoring servers to know that it's in the cluster partition that has the majority, it will see servers and it will make that partition of the cluster not allow write and read attempts any longer until the required amount of monitoring servers, which is at least 50% plus 1, is functional again. Monitoring servers also keep record of all existing monitoring servers and all existing OSDs and create documents containing exactly this information for the clients to use. So the monitoring servers create a file called monmap and they create a file called OSDmap, and these 2 files are handed over to clients if the clients request them. And last but not least, by doing so, monitoring servers are the initial point of contact for clients in Ceph. Every client that wants to talk to OSDs needs to talk to a monitoring server first
to get a list of the existing mons and to get a list of the existing OSDs. And only after the client has received these information, it can talk to OSDs directly. So monitoring servers are not proxy servers, but they allow clients to figure out what the state of the cluster is. And as soon as they have received these information, they can talk to OSDs. Let's take a closer look at how data placement in Ceph exactly works. How does a client that wants to store data in Ceph actually do that? What is the process going on there to bring information, to bring data actually stored by the client onto the Ceph object store? We have our OSDs. Obviously, in this example, we only have 4 OSDs. In real-world clusters, we will obviously have many more of these distributed amongst really a big number of clients. You will need at least 3 monitoring servers for a working Ceph installation, and you can have an arbitrary number of OSDs distributed over numerous servers. We have the monitoring service per se, so these are responsible for taking care of the actual cluster tracking, figuring out what the status of the cluster is. And last but not least, we have the client trying to upload the file that we have seen earlier already. Now, there is a shadow over the OSDs. I will get to the idea behind this in a minute. As I have explained earlier, the client needs to figure out what the status of the cluster is before it can use it. So the client needs to know which OSDs exist and which monitoring service exist before it can in fact use the cluster. What the administrator will do in this case is whenever the client tries to access our object store in this case, the client will contact one monitoring server first, and this is the only time that the administrator needs to specify an IP address to contact. So the client now has this IP address given by the administrator. The administrator will then, the client will then connect to the monitoring service, or at least to one of them, and receive the information on which OSDs we have and receive the information on which monitoring service we have. As soon as that information is present on the client knows which OSDs are present in this cluster and where it can go, where it can actually upload the information it wants to store. So the client now knows what the cluster looks like, and the next step the client needs to perform is it needs to cut the object, the file it wants to upload into the object store into the binary objects. It needs to create these binary objects from the original file. Standard size for one binary object in Ceph is 4 megabytes. So imagine the file we are trying to upload has 16 megabytes in size, and the client will actually cut this file into 4 binary objects being 4 megabyte large each, which by now is in fact already the process of cutting the binaries, or cutting the file into binary objects. The client now knows what the binary objects will be, and the next step the client performs is it assigns the binary objects to groups. So what the client basically will do, it will declare that the first 2 objects on the left belong to the green group, and the second 2 objects on the right belong to the blue group. These groups in Ceph have a special name and they have a special role. These groups are called placement groups, and based on placement groups, the client can determine which OSD it needs to upload the binaries to, the binary objects to. So by actually assigning the binary objects to placement groups, the client at the same time figures out which of these binary objects will make it onto which OSD. Binaries belonging to one placement group will be stored on the same OSD. So now that our client has done the actual cut of the binary object and the client has assigned them to placement groups, the next step would logically be uploading these objects. The green placement group will go to OSD number 1. The blue placement group will go to OSD number 3. And now what the client does is it starts to upload the binary objects, which is somewhat nifty because it does that in a parallelized manner. The client will upload as many binary objects to the OSDs as it can. So whether the network is the bottleneck here or the actual hard disk performance really depends on the local hardware. However, the cool thing in this case really is that this happens in a parallelized manner. So the client is writing to many spindles at a time, it's writing to many hard disks, and by that can generate more performance, can get more performance when writing than it could get if it's writing to one single hard disk only, because it's writing in a parallelized manner to numerous different hard disks present in this cluster. This is of special interest if you are trying to create a setup that is cost effective, because you won't need fast SIS disks. You can create a setup with Ceph based on standard serial ATA disks. And these, in fact, can be any arbitrary serial ATA disks from any standard computer store. All you need to ensure is that these are present in the service. Which of course also means that typically you can use bigger serial ATA disks. You can easily use 10 3 terabyte serial ATA disks for a Ceph setup where you would otherwise have to use 300 gigabyte SAS storage devices to gain comparable speeds. By using just one example from the everyday administration, by using standard serial ATA disks, we have been able to gain write throughputs of about 300 megabytes per second. So this really depends on what the hardware on the client can do. If the hardware is connected to this only via gigabit Ethernet, then obviously the bottleneck will be in the network layer. If the client is connected via 10GE, in fact, the bottleneck is probably still going to be the disks on the actual OSDs. So let's take a look at the situation as it is right now. We have the green placement group assigned to OSD number 1. We have the blue placement group assigned to OSD number 3. And as I have explained earlier, we have internal redundancy in Ceph, which means that Ceph is going to automatically take care of replication for us. All we need to do is tell Ceph how many replicas of the objects we want. The standard configuration here is 2 replicas, so every object will exist twice within this cluster. And another nifty piece of information here is that the actual replication happens based on the object storage daemons. So what's going to happen next is that the object storage daemons, which now hold the initial copies of our objects, will start to replicate those to the other object storage daemons present in the cluster, ending up with a scenario that looks like this. We now have the standard replication policy fulfilled. We have 2 replicas of every object, and in fact the write process done by the client is now finished. So this is the step where the client receives the write and containing information, where the client receives the OK for the write attempt, and the client can just carry on with doing whatever is supposed to be done next. What we have not discussed yet is the question of how exactly the client determines which OSDs are going to hold a single placement group, which is of interest because, as we have already said, the client only needs to upload the object once. So if there are 3 replicas required by the replication policy defined by the administrator, the client still needs to upload the binary object only once, and the rest will be dealt with by the OSDs themselves. But how does the client determine exactly which OSD to upload an object to? I mentioned the fact that this is related to placement groups. So by assigning the objects to placement groups, we are in fact already doing the first step. Now, how does Ceph determine which OSD a specific placement group needs to be uploaded to? This is where Crush comes into play. Crush, in fact, is an algorithm. Now, it's certainly debatable whether it's a good idea to call an algorithm that deals with data Crush, but in this case, it really just is another acronym. Crush is an algorithm written by CephFS. So, in fact, it was specifically created for Ceph. It's an invention by the Ceph developers, and the whole assignment between the OSD, the placement groups, and the actual object happens based on this algorithm, which is important because it means there is no hash table, there is no database where you store information on which object resides on which OSD. In fact, all this happens completely based on the Crush algorithm. I mentioned that Crush is an acronym. Crush stands for Controlled Replication Under Scalable Hashing. And that is just what it does. The developers call it pseudo-random because, in fact, the result produced by the client when calculating the target OSD for a binary object is random at once, but it's reproducible. So if you do the Ceph calculation, or if the client does the same calculation for the same object 10 times, it's going to get the same result 10 times. It is, however, not the case that there is anything stored statically in this progress. So it doesn't have to store the information which OSD it uploaded an object to in the first place. It's just a case that the algorithm produces the same result again and again whenever the client does this calculation. The cool thing about crush is that for the administrator, it's possible to modify and to influence the crush algorithm, which in fact is what you would do if you want to make Ceph rec aware. The crush algorithm allows the administrator to define own requirements for data replacement. So let's say you have 3 data centers and you want to make sure that Ceph stores one replica of a binary object in every data center that we have. You would modify the crush map, the crush configuration, to achieve exactly this goal. Let's say you were having a 30-node Ceph cluster distributed across 3 data centers, and you wanted every binary object to exist 5 times in every of your 3 data centers. Then that is also something you could achieve by manipulating the crush map. If talking about smaller scaled setups, obviously you could also use this to distribute several copies of your objects amongst different fire zones in your data center, or amongst different racks in the area of the network, maybe connected to different uplinks. Fantasy really is unlimited in this case, but it is fairly easy to create a very fine-grained definition and configuration of where you want to upload which object into your Ceph object store. Let's talk about clients. Up to this point, I have only been speaking about the actual object store. Now let's see what technologies we have on the client side. How can we access the Ceph object store that we have? Because obviously without any client software, the object store would be pretty useless. So let's take a look at what exactly we have. First of all, what we have is we have a block device driver. So we have a driver in the Linux kernel that allows us to access a Ceph object store just like we were accessing a local standard block device. That driver is called RBD. RBD is the acronym for Rados block device, and RBD comes in 2 flavors. The first flavor is the actual kernel module. So if you have this driver in your kernel, what you can do with RBD is you can just create an RBD device, a virtual RBD device that is, by the way, fin provisioned, and create a file system on top of that and enable that Rados block device on any client you are using. You will just have a /dev/rbd0 then, and you can access that file like you could access any other block device present on the local machine. You can even access it from numerous clients at the same time. So we have seen installations using OCFS2 or GFS2 on top of RBD, which probably is not the best thing to do, but technically it's possible. The RBD kernel module is part of Linux. It's upstream since Linux 2.6.37. And as already said, RBD devices are fin provisioned. So if you create a virtual RBD image that is like 100 gigabytes large, it's only going to use 100 gigabytes in your object store if you actually upload that amount of data into it. The second flavor we have is QEMU-RBD. QEMU-RBD is a storage driver for QEMU that supports the RBD protocol and which in fact allows you to access any RBD-based information, any Rados-based information from within QEMU. So what you can do is you can start virtual machines having a hard disk, having a block-based storage device that in fact resides in Ceph. You don't need to use the RBD kernel module for that because you have native RBD support in QEMU. And with that native RBD support, you can in fact build virtualization clusters where the storage itself and the actual virtual machines are all running on the same hosts. So what you can do is you can build self-containing virtualization clusters, like the one seen in this picture. We have 8 servers here. Obviously, again, we will have numerous OSDs per server, not only one, but I painted one here per server only for reasons of making the figure a bit easier to understand. And in this cluster, in this setup, every server, in fact, can run every virtual machine that is stored inside Ceph. No matter which of these clients fails, you will only encounter a downtime if the client that failed actually run the virtual machine, but right after that you can restart the virtual machine on any of the other servers that is present in this installation. What we also have is we have a RESTful API. RESTful APIs are something that is very hip at the moment because it allows you to provide users with HTTP-based access to your object store. That is something that is taken care of in Ceph by radosgw, the Rados gateway. The Rados gateway is in fact made for online storage offerings like Dropbox or Google Drive, if you know these solutions, and is made to offer users the ability to upload files via HTTP. So whenever somebody wants to upload something to an online store, that is what you can do in Rados by using the Rados gateway. Rados gateway is FCGI based, will typically be deployed in conjunction with Apache, and any FCGI capable web server, however, will do as well, so you don't necessarily need Apache, but Apache and mod FCGI certainly is the standard solution to go. Even if it doesn't look like that here in this figure, in fact, the Rados gateway is not a single point of failure. The Rados gateway scales out at ease, just like any other component we have in Rados. So if you don't want to have only one of these Rados gateway servers, you can have 10 of these as well, or 20 in combination with a load balancer. You can easily create setups that have no single point of failure. The Rados gateway is compatible with Amazon S3 and Swift. So in fact, with the Rados gateway, you can use any other software that speaks the S3 and the Swift protocol. Which means that particularly all clients available for Amazon S3 are going to work together with the Rados gateway. You can also use the Rados gateway with a Ceph-based storage in the backend as a replacement for OpenStack Swift. So if you have OpenStack Swift and you want to replace that with Rados, then that is possible via the Rados gateway as well. Which brings us to the last really interesting client, and that is something that definitely is the one with the most PR at the moment, CephFS, a POSIX-compatible file system that uses the Ceph object store in the background. In fact, this is what everybody keeps asking for when it comes to using Ceph, because it's a wonderful way to work around the requirement for cluster file systems or any of the other solutions that we have out there. Using CephFS in Ceph is fairly easy because, in fact, all you need in addition to object storage daemons and monitoring service is a third service that's called metadata server. The metadata server is the service that is responsible for delivering the actual POSIX-compatible file system information to the clients, which is a concept that some of you might know because that is something that is, at least when it comes to the words, comparable with Lustre. However, in Lustre, the problem is that the metadata servers, in fact, contain information. So they store information, and if in Lustre you lose the metadata server, at least the current version has these problems. I think this has been fixed in an upcoming version of Lustre. However, at the moment it still is that way. If you lose the metadata server in Lustre, then you will encounter downtime because you can't have a real replacement for it. In Ceph, the actual metadata information for files stored in CephFS are stored in the user extended attributes of the file system. So if the metadata server, for whatever reason, fails, then you just have a standby metadata server that probably will react a little bit slower at the beginning, but it will heat up its cache, and then you will just have the same fast access to your POSIX file system metadata information you had before. Which really is cool because you can start as many metadata servers as you want, and whenever the one you are running fails, you can just as easy use another one there. I guess it's a good idea to just think of the metadata server in Ceph like a big cache for POSIX-compatible file system information. I guess that's the easiest way to keep in mind what the metadata servers are. So the only problem we're having with CephFS, it's still beta. It's officially not declared done. There's still some work happening on Ceph. In contrast to all the other pieces of software, to all the other components of Ceph I have just mentioned. In fact, this part of Ceph, of the Ceph storage stack, still is in beta phase. The file system per se has been part of Linux ever since Linux 2.6.32. It's still marked as experimental, at least in any kernel up to Linux 3.8. In 3.9 it's not going to be flagged as experimental anymore, particularly because not it had become stable meanwhile, but because the experimental flag was removed. So please don't be fooled by that one. As said, it's the only service in Ceph at the moment that you cannot get any commercial support for because it's still beta. The other components we have in Ceph are declared done officially, and you can just use them in a commercial way in your standard setups. If none of the clients I have mentioned up to this point suit your needs, what you can certainly do is you can write your own client if you want to. There's a C library available for this. It's called librados. And librados allows immediate access to the Rados object store based on the programming level. Librados, for example, is the part of the setup that the QEMU RBD driver uses in the backend to use access or to get access to the Rados object store. By the way, librados also comes with bindings for numerous scripting languages. We have a language binding for Python. Interestingly enough, we have PHP Rados, which means you can access Rados right from within PHP applications, which may sound strange, but is not so strange if you imagine that you could just have your PHP application upload any information right into Ceph instead of storing it in a file system first. And by using any web interface or by using any web application that can do file storage right via Rados, you could simply work around the need for any file system in between there. What are the use cases that we have? What can we do with the storage solutions like Ceph? Well, first of all, obviously, this is a solution made for gigantic storage. If you want to do something like this, you could get a 40 terabyte storage with 3 replicas, meaning that every object exists 3 times for around about 21,000 euros. And this is the standard list price of hardware. So if you have a standard hardware seller, if you have a standard hardware vendor, and you can get the service for less money, you would probably be able to get this for an amount of money that is substantially smaller. Obviously, a very common field of use for this is virtualization. I have just mentioned virtualization. Thanks to the perfect connection between QEMU and RBD, it's very easy to create self-containing virtualization clusters, having storage and virtualization in the same service. iSCSI storages are an alternative for Windows servers. So if you have Windows servers that need iSCSI to do their storage stuff, what you can do is you can use RBD and run an iSCSI target on top of RBD, have your Windows clients connect to the iSCSI storage, and that way your clients will connect to iSCSI, will connect via iSCSI to your Rados cluster and store their data in Rados. Cloud, really important. You're my witnesses. I have mentioned this word. Everybody needs to go into the cloud. So object storage solutions like Ceph obviously are made exactly for this purpose. And we're talking about the cloud. Let's throw a quick light on OpenStack because OpenStack is really well integrated with Ceph. We have the core components of OpenStack, Glance, and Cinder, which need storage in the backend, and we have native interfaces for Rados in both of them, so we can connect OpenStack Glance and have it store its images right in the Ceph installation. We have Cinder, and we can have Cinder have as a block storage service, storing the information it is supposed to store right in Ceph in the backend. And as I have already mentioned, we can also use Ceph as a drop-in replacement for OpenStack Swift via the Rados Gateway interface. So if you plan to replace your OpenStack Swift installation, then that is possible as well with Ceph. Which, in fact, we have done, and we can confirm that this is working in a very well manner. There have been some improvements in OpenStack recently with regards to RBD, and this is something that you can really use to create a very reliable and very stable storage backend for OpenStack that actually will scale out. Which brings me to another question I would like to ask. After all the information that I have just bombarded you with, who of you believes that this must be utterly complicated to set up and really hard to do? Okay, so we have a bunch of geniuses in here. That's cool, okay. I would like to demonstrate it anyway, because I still have some 5 minutes, I guess. Let's just do a quick presentation of how you can actually use this. We have 3 virtual machines running here on my notebook, so this is not going to be super fast, but please bear with me for the moment. We have Alice, Bob, and Charlie. In fact, we have one Ceph configuration file. The Ceph configuration file is usually stored in etc ceph.conf. We will see, oh come on, I love that. We will see that the configuration file per se is not very complex. We have a CephFS paragraph in here enabling authentication between our Ceph nodes. What we can do here for security reasons is we can make our Ceph nodes connect to each other only after they have identified them with a password, which allows us to make sure that nobody puts something into this cluster that doesn't belong there. We have a monitoring section here. The monitoring section defines which hosts in this setup are going to have a monitoring server running. We will have all 3 servers here running a monitoring server because we can. We have the metadata paragraph. The metadata server paragraph does the same thing for metadata servers, so it defines which hosts of this setup will be running a metadata server. And then we have our OSD definitions. This is really, really easy. I mean, it's just having a general OSD paragraph. It's having general OSD entries there. We'll have OSD 0, OSD 1, and OSD 2, hosted on Alice, Bob, and Charlie. And last but not least, we define where to find the client admin credentials required for anybody to log into this cluster with administrator privileges, because obviously it doesn't make much sense to have the servers identify against each other with a password protection if we don't do the same thing for administrators. And with this Ceph configuration in place, I don't really remember how many lines it has, but I think it's really just something around the 30s. Okay, so it's 44 lines, and this is the complete configuration we need for Ceph. What we can then do, if we have this configuration, we can simply call make CephFS. This is the, at least at the moment, the standard setup tool for Ceph. So it's one command line we need. Can the guys in the last row see this, or is this? Okay, good. All we really need is this command. It's make CephFS. And if we do that, then make CephFS is simply going to set up the Ceph cluster on behalf of us. As soon as it's done with that, what we can do is we can start the Ceph cluster. The init script contained in Ceph allows us to start all these services on all machines at the same time, but you don't have to do that if you want to stop them or to start them on the machines in a controlled manner, one after another, then obviously you can do that as well. And right after this, what we have is we have a working Ceph cluster that is now ready to provide us with services. We can use it right away. We can use CephFS on behalf of this right now. We can use RBD on behalf of this right now. If we had to use the Rados gateway, we would still need to set that up separately, but the 2 core services provided by Ceph now are ready for action. We can actually demonstrate that. We can do a mount. Here we can mount the CephFS that we have on this machine. We can mount that to MNT Ceph. And as you can see, the directory is empty. Now, what we can do is we can do we can create a file that is called test. And now if we copy the actual secret key for the administrator over to Bob, we will be able to do exactly the same mount on Bob again. And once we have done that, we can see that now we have access to the same file on Bob as well. and the file is just the one that we have created on the other node. That is for CephFS. Let's imagine we wanted to use RBD. That is fairly easy as well. What we need to do is we need to create an RBD interface. In this case, it's just 1 GB large for demonstrational purposes. So we need to create the RBD interface. The next step we have to do is we have to map it. Mapping, in fact, means enabling the RBD device on the local server. As soon as we have done that, we can see that there is a def RBD 0. And now what we can do is we can create a file system on that one, and we can mount that on the local server as well. And we could just do that on any other of the nodes we have. It's not necessary to have RBD active on only one node of the cluster. You can activate one RBD device on as many cluster nodes as you would like to. And that is the file system that we have just created. So long story short, if you are willing to try Ceph, all you need really is 3 virtual machines. It's not going to be super fast, but it's going to give you a first impression of what you can actually do with Ceph. The software you need is available freely from the Inktank repository. Packages are available for Debian, for Ubuntu, for SUSE, and for Red Hat. I think for Red Hat you will need Red Hat Enterprise Linux 6.4 or something later, and you can just go ahead and test these things then as you would like. If you have free hardware service you can use for testing, you might be able to get some more appropriate values of what the hardware and software in this case can actually do for you. And apart from that, I hope the information you received today were helpful for you. Let's do a round of questions, I guess.
Just ask because you didn't through this.
Okay. So let's start there, okay?
Yeah. Can you go back to the page where we share the file paths to the OSDs?
This one you mean?
Yes. Just one more. Yes. Okay. If I bring my clean bullets to the first OSD.
Yeah.
Say, okay, I have the data.
Yeah.
Now, my first OSD correct.
Yeah.
It's no replication because you said you don't need to break. What happened to my clean bullets?
Well, if the okay. So first of all, what is important to know to answering that question is the write process within Ceph is only going to count as finished if the actual information that need to be written to the OSD have hit the OSD journals of as many servers as the replication policy defines. So if you have a write process that is writing to your disks, the actual process will only count as finished as soon as the data have hit the journals of 3 OSDs if you have a replication policy that demands 3 replicas. If your primary OSD crashes before it has been able to actually create the other copies of your data, the client will not receive an OK. So the client will know something has gone wrong while storing this information, and it will have to redo the write attempt.
Exactly the same slides between the client and the OSDs. Is there some sort of encryption in between?
No, not at this point in time. I know that is a feature request that has been brought up by many people to Inktank numerous times, but at the moment there is no way to have end-to-end encryption in this installation.
And one additional question regarding the Ceph configuration, because it seemed quite static. So if I want to add an additional OSD, for sure I have to roll out a new Ceph, but to restart the complete cluster.
No. Ceph.conf in fact is a very statical file, but Ceph.conf is not what the Ceph services gather the information from the actual state of the cluster. We have the monitoring map, that is the current up-to-date directory or file containing information about the present MON servers. We have the OSD map, that is the file that contains information on which OSDs we have. And if you want to add a new OSD to this cluster, you would need to deploy a new ceph.conf, but you wouldn't have to restart any OSD services, because when adding the OSD to the cluster, what would happen is that you, by adding the OSD, tell Ceph, please adapt the OSD map accordingly to know there is a new OSD. So there is no downtime involved when adding new OSDs. OSDs can be added and removed at ease during the normal operation.
Also is some redistribution or just new empty OSDs then?
If you add an OSD, there will be no automatic redistribution. What is going to happen is that the new OSD you have will be integrated into the crush map calculation, or into the future crush map calculations, but Ceph will not, unlike, for example, OpenStack Swift does, start data shuffling in order to be rebalanced again. That is something that is not demanded in Ceph, in fact. There are some benchmarks available from Inktank concerning exactly this subject. I know there is a report on performance between, for example, ClusterFS and Ceph, or CephFS for that matter. I think there is one for Ceph and OpenStack Swift. What I would recommend to gather this information is there is an Inktank blog, and if they do benchmarks, it's fairly probable they will put the results up there. So go to the Inktank blog and search for a benchmark there, search for a benchmark comparison there, and you will already find numerous entries concerning this, and future ones will be added by sure. There's Mark Nelson, who is the community manager of Inktank, and he's uploading stuff like this in quite a regular manner. I think you should find something concerning ClusterFS in the blog. I think there has been some posts about this. Sorry, which one? I'm sorry, but I didn't understand. Okay. I don't know if there's anything existing for this comparison just yet. I don't even know if somebody has tried that up to this point. But what I would recommend doing in this case simply is writing some sort of request to Inktank and telling them, okay, this might be interesting to have a comparison between, and usually they will react to such requests rather quickly. You were first.
It's a question about if you have added new OSDs, because you have a new hardware generation, you get faster disks. Is it possible to manually redistribute certain objects? So you say, this type of files I need now with more performance.
Yes, you can move placement groups, which is the feature you're looking for. Moving placement groups from one OSD to another is possible.
How are objects addressed? So
What exactly do you mean?
What is the input to the crush algorithm?
It's the actual overall amount of number of placement groups, which is I think 768, and then it simply is the value resulting from the random function used with the name of the actual file you're uploading. I can give you the technical docs for that if you're interested in it.
So an object has a name.
Well, every file you upload into this has a name, yes. Ceph, in fact, is a flat namespace. And every object itself has a name. Everything you upload from the client side has a name as well, obviously.
So there are multiple clients connected.
Mm-hmm.
So the crush algorithm makes sure that if you try to create objects with the same name, that gets mapped to the same OSD.
I think you cannot create objects with the same name in the same pool. One thing that I have not mentioned yet, because it would just have made things more complicated, is that Ceph internally is split into pools, which in fact are name tags. So What Ceph supports is you can, for example, tell Ceph, I want to have different pools, and you can restrict access to pools to certain users, which is good for for privilege separation. And I think you can have one object with a name, or you can have one file with a name only once per pool. Okay. Yes, please. The monitoring service, in fact, store the secret keys they need for CephFS. The monitoring map, so the mon map is not stored statically. If you have one monitoring server left, it will claim it doesn't have quorum, but it will still contain the last copy of the monitoring server. If you start the cluster from scratch, if you start everything new, the first monitoring server present there will start with a new empty mon map. And just rebuild it depending on the clients that get added. We can in fact see what Ceph currently thinks just by doing Ceph health. I think that's going to be okay. So let's start with Ceph -w, and the first batch of information you have here tells you which monitoring service are part of the mon map, which OSDs we have, and which metadata service we have. There was one other question?
Yes. If the client splits the objects into these chunks,
Yep.
is there a kind of compression?
No.
Can it be?
You can configure it. I guess it's another feature that would be interesting to be directed towards Inktank, but right now there is no compression integrated into this.
Does that support like
Snapshotting is integrated for all clients that we have. CephFS supports snapshotting, RBD supports snapshotting, and the object storage Ceph supports snapshotting as well. In CephFS, creating snapshots is as easy as creating a folder that's called .snap in the same directory, which will create a snapshot of the thing. Copy on write is possible as well. I think it's supported in Ceph Bobtail, which is Ceph 0.57. So yes. Yes, please. No, in fact it does not, because locking in Linux file systems is something that is a topic not so awesome, particularly because almost no file system present for Linux at this moment supports mandatory locking. What CephFS supports is advisory locking, so anything that uses flock or fnctl is just going to work. However, there is no reliable way to avoid that a client overwrites a file that another client has open right now, just like with any other standard Linux file system that's present. So no, CephFS does not support mandatory locking, but it supports advisory locking. Okay, so yes, please.
The debugging is really a headache over there. For instance, when you are trying to find out which client is connected to the meta server, which one generates the most of the traffic, this is a kind of painful task. Is it painful?
Ceph includes a collector D integration, so you can get numerous statistic information out of Ceph that way. I do know there are plans to make that even better. I don't know exactly what concrete information you can get out of this, because it's just it's screen pages full of information. But I'm fairly sure that you can find out which clients are connected to this thing at the moment.
Well, which clients are connected to the program?
That is something you can find out via the send messaging queue information in that output. I can give you the commands for that if you want to have them. Okay, so if there are any more questions, I think we're slowly running out of time. Please find me somewhere during the rest of the conference. I'll be here today and the rest of tomorrow. And apart from that, thank you very much for the attention and have a good day.